Now we'll do some practice problems from chapter 21, the second part, which is the electric field. So if I look at question 17 says, if you have two charges here, you have a Q capital charge and it's negative, -6 nanocoulomb, and a Q small is positive charge, 3 nanocoulomb. What is the electric field at point P here? And Q capital, Q small, the charges are arranged this way. So you have the distance from here, if you think of this 0, 0 to Q1 is A, from here to Q small is A as well, same distance. And this is the distance B from the center, from 0, 0. So to find the electric field, remember, we have to think of vectors of electric fields at point P. So what we should do first, we have to think that there is an XY here, and we draw the effect of this charge Q1 here, the direction first, and here this one as well, its effect here. So we'll assume there's a positive charge here, and we draw the vectors here. Once we find the vectors here, the directions, then we find the magnitudes only for each point charge here, and then we think of finding the total vector. So to solve this question, what we can do is we draw the point charges, just a sketch. So I'll assume that here I have this arrangement. Here we have Q capital, which is negative, and here we have Q small, which is positive, and this is point P. This is A and B, A and A, sorry, and this is B. So what is the first step is we imagine there is, this is question 17, we imagine there is a positive charge here. So what's the effect of this negative here? It's attraction. So if I think of XY here, I'll have a vector of E this way, which represents the total of Q, electric field, positive, negative. Now here we have positive, positive, we have repulsion, so on the line of action here, you'll have E for Q. So you can see here we have two vectors of electric field, first one in the first quadrant, second one in the second quadrant. What we have to think of is, first, what's the distance between them? So if I call this one R, the distance between the point P and Q, and of course you can see that this one has the same R. So if I find one of them, I find both, and this can be found by using the triangle here. Now this angle, if you look at it, this angle, if you call it theta, you can find it by knowing these sides. And remember, A is 0.6 meters, so 60 centimeters. B is 0.8 meters. And the charges are, you have Q capital, -6 nanocoulomb times 10 to the power -9 coulomb. Q small is positive, 3 times 10 to the -9 coulomb. So now we need to find this angle. The angle can be found by sine or cosine if you know A and B. Now this angle as well for this vector same as this angle. So it's theta as well. So if you find one of the theta, you can use it for both. Now what we need to find now, R, you find it by Pythagorean theorem, a square plus b squared, and you find that when you substitute these values is equal to 1 meter. So R, the distance between both. Now the next step is to find the electric field of each. So, the magnitude of electric field of any point charge is equal K, constant, the charge over distance square. So if we apply this one for the first charge, you'll have the magnitude of Q is K, Q capital over R square, and for the small one, the magnitude of the vector is K, Q small over R square. Remember the R's are the same, but the Q's are different, so you have different values of E. Now, once we know the electric field magnitude, then we can think of the component, because for each electric field, let's say for Q, this has two components, has X component, Q, X, I, and it has E, Q, Y, J. Same for small one, it has E, Q, X, I, E, Q small, Y, J. We don't need to use the I and J, but this is just explanations of the directions. So if I want to draw here the component, you can see the EQ has two components. So if I remove them here, this is point P. This EQ will have EQ cosine theta, if I think of this theta, sine theta. And here we have EQ sine theta. Same for EQ capital. We'll have EQ cosine theta. If I think of this theta here, we don't have to worry about the direction, negative, positive. We just take them as they are, because we are interested in the magnitudes. And EQ sine theta. So now I don't need the original vectors. You can see now I have two components on x-axis, they are opposite. So the total x, if I want to find the E net, the total, the magnitude of the total vector, I have to know E net on x, which is the I, plus E net on y, which is the j. So we need E net x, E net y. Now here you can see the E net x, you just have to subtract. But for E net y, I just have two components, both in the same direction, so we add them. We add these two, but here we subtract. So we find E net x, E net y. Once we find these, we can find the magnitude of E net x, E net y, and then we find the magnitude of E net total. So here we say E net x, the magnitude, of course. You just say large minus a small. Of course, this is larger because the charge EQ is bigger and it's the same distance. So here we say EQ cosine theta minus EQ small cosine theta, and gives you the total. For E net y, same, but here we have to add them because they're in both directions. So you have EQ sine theta plus EQ cosine theta. and you get the total. Once we have that, we say E net total is the E net x squared plus E net y squared under the root, and you get the value which is given. Now I'll show you the page which I solved it in detail, but just remember it's all about vectors. Yeah, you find the total on x, total on y, and then you do the Pythagorean theorem to find the final answer, which is 53.2 Newton. So now this is the detailed solution. Of the question. You can find, of course, the sine theta and cosine theta, or you just have to find the theta once, and then you can find the component. So you have the EX net subtraction, E net Y, you add them, you get the E net X and E net Y, and then the Pythagorean theorem gives you the total electric field. Right, now let's look at question 20 from the practice problem, chapter 21, electric field. Now the question says a charge Q, positive charge, 40 microcoulomb, is positioned on the x-axis. So this is the x-axis at x equal 4 centimeters. So this is 0, 0, and from here to there 4 centimeters. Now the question says, where should a charge Q, capital, which is negative, minus 60 microcoulomb, be placed to produce a net electric field, a total electric field of 0 at origin point? So here we want an electric field here to be 0, the total. Now if you want total electric field to be 0, it means you must have the electric fields opposite, so they can cancel each other, equal and opposite, and they must be both on the x-axis, because the first charge on the x-axis, so the other charge must be on the x-axis somewhere here to cancel out. So what are the possibilities for the position of Q capital, which is negative charge? Where shall we put it to have an electric field of 0 equal to 0 here? Now what we do, we imagine there's a test charge here, and then we take the effect of this charge Q, which is positive, and Q, which is negative, okay, and we test. Look here, we have 3 regions to test. Either Q capital is on the negative x here, that's region number 1, or between 0 and the Q, region number 2 here somewhere, or behind Q small here, region number 3. So we'll test all 3 and see what are the possibilities. So let me show you that here in the drawing. Okay, now let's take the first possibility that Q is in this region here, Q capital. Remember, Q capital is negative, this charge is positive. So what's the total electric field here? What we'll do, we'll imagine there's a positive charge here, test charge. It's a test, small one, there's no real charge here. Now what's the electric field of this charge here, and which way it is? Positive, positive, you have repulsion here. So the electric field EQ will be this way, small q. Now this is negative charge, this is positive charge. The electric field of this one, or electric force, attraction, so it will be in the same direction. So here it's not possible to have a total equal to 0 because in the same direction. So this option is out. Now let's take the second region here between 0 and the charge. So if I imagine there is a Q here, anywhere here, not exactly halfway, say suppose it's here, it's a Q capital and it's negative. What are the possibilities? Again, I assume that there's a positive charge here at 0, 0, testing charge, negative, positive, so the electric field of the Q capital is this way, EQ capital. Positive, positive, repulsion, so it's this way. This is EQ small. So here, what do we have? We have two electric fields opposite. So is it possible those are equal to 0? Yes, because we subtract. But you can see here that Q small is 40 microcoulomb. Q capital is 60 microcoulomb. So when you put a Q capital between 0 and a Q small, its distance to the 0, 0 is small. So when R is small, the electric field is large. That's number one. What else? Q capital is bigger than Q small, 20. So the possibility is that EQ capital is always larger than EQ small, wherever you put it here. So again, this possibility is out. So we have to waiver this possibility. So the last possible position is behind Q small. So if we put it here and it's negative, we imagine there is a positive test charge here. Positive, positive electric field is this way for Q capital, for Q small. Negative, positive attraction. So this will be EQ capital. And you can see they are opposite. So there is a possibility here they are equal to 0, because here you have to subtract. And because the Q is far away, this distance R2 is larger, but the distance is bigger than R1, so there's a possibility those are having a net equal to 0. How do we solve? We just have to say the magnitude of electric field of Q small must equal the magnitude of electric field of Q capital, and both of them are point charges, so the electric field of Q small is KQ over R1 square. This is R1 square, which is the 4 centimeter, and for the capital, which we want how far it should be, KQ capital over R1 R2 square, and remember R2 is the unknown. Here you can cancel Q with the Q, and we substitute for R1 and the Q, of course. You have 40 here. R1 is 0.04, change it to meter square. Q capital, we don't need the signs because we're talking about the values. 60, and remember these are micro on both sides, so even if I multiply by 10 to power minus 6, it will be cancelled from both sides, and this is R2 square. So here you have micro, they cancel each other, and the only unknown is R2, and do the math. Here you find that R2 is equal to 0.049 meters. This is where you should put the R2. Here I'll show you the solution. is the final solution. Right, now let's do question 21 on electric field. Question 21 from the practice problem. What we have here, we have two charges, Q1 and Q2, and both are positive. Q1 is 77 microcoulomb at a distance of 4 centimeters from 0, x value. Q2, 50 microcoulomb placed on the y-axis, 3 centimeters from 0. Okay, so now we have x and y. The charges they are not on the same line. They are in 2 dimensions. The question says that both charges were held fixed, so you don't let them move. They are fixed in position, otherwise they start moving, attracting or repulsion. Here of course we have repulsion, they repel each other. So those are fixed in position. Now the question is, what's the magnitude of the initial acceleration of an electron released from rest at origin? So the question says, if you put an electron here, remember electron is a negative charge, at rest, you don't fire it, you don't push it or pull it, you just position it here at rest, starting from rest at origin. What is the initial acceleration of the electron? So what is the acceleration of the electron? Right, at origin. The electron has a negative charge, of course, and we have to see the effect of these two charges on the electron. Now, what we can do here, we can imagine that there is a test charge, positive here, instead of the electron. Okay. And we see the electric field of Q1 here, and electric field of Q2 here, and we find the total electric field here, the total electric field or electric field net here. Now, once we know the electric field here, then we can find the electric force net. What's the total force, electric force on the electron? We can replace it now with an electron. Of course, you can keep it as a positive test charge, but remember, once you talk about an electron, you have to reverse the direction of the force, because here we'll find the electric field total, not the electric force total. So we'll assume there's a positive charge here, test charge. We find the total electric field. Then once I have the total electric field and I have the charge, which is the charge of one electron, I can find the total force, electric force here. And if we know the total force, F net, from mechanics, from physics 1, you remember that Newton's second law says that if we know F net and we know the mass of an object, of course we can find its acceleration. And here the total force can be found. So what shall we do first? We'll find the electric field directions. So we'll assume, it's Q1, Q2. I'll assume there is a positive charge here, test charge. What does this charge do here? Electric field is directed this way. So this will be EQ1. I'll call it E1. It means charge 1. E1. This one as well. Positive, electric field E2. If I know the magnitude of this one and magnitude of this electric field, I use Pythagorean theory. It gives me the E net. So here you can see that E net is between these two electric fields. So the steps are like that. You find E1 magnitude due to the Q1, E2 magnitude due to Q2, and then use Pythagorean theorem to find E net. Once we find E net, then we can find F net from the formula of electric field definition, but we replace the positive with a negative charge. So here we put negative, which means we have to replace the force. So the electric force total is not in this way, it's the opposite, so it goes this way. Okay. This would be total force F net, because the charge is negative. Here the charge is positive, the test charge. Here the electron total. But it doesn't matter, here we just want the magnitude. So step number 1, find E1. How you find E1 magnitude? K Q1 over R1 square. And here R1, it means the x-axis, the x value. And x value is 0.04 meter. It's 4 centimeter. So we just have to substitute K, Q, 9 times 10 to the power 9 times 77, and it's a micro minus 6 over R1, which is the x square. This is E1 value. E2 value, same procedure, K Q2 over R2 square, 9 times 10 to the power 9 times Q2 is 50 times 10 to the power minus 7. Don't forget, don't put the signs here, positive, negative, although both are positive, but we need the magnitudes only. R2 here, it means the distance from here to there, which is the y, and the y is 0.03. So once you know E1 and E2, then you can find E net. And E net value, because those are at 90 degree, so it's like I and J, so this is the total. You just have to square both values. So you'll have E1 square, which is on the x-axis, plus E2 square, which is on the y-axis under the radical, and you find E net total, which is 6.61 times 10 to the power 8 nanocoulomb. Now we know E net, and we have a charge here. So if you know the total electric field here, and you know the value of the charge from the definitions of electric field is equal to the force over the charge. Here your test charge is an electron, so, and the force is electric force, and it's the only force here, which is F net. So if I want to find F net, I just have to multiply the charge of an electron, Q electron, multiplied by E, and E here is E net. E net, the total electric field, which is this way, E net, but we reverse it because it's an electron. So E is known. Charge of an electron is 1.6 times 10 to the power minus 19 coulomb. Again, don't put a sign because you are after the magnitude, so don't put the negative sign here. And electric field is 6.61 times 10 to the power 8, and this will give you F net. F net is 1.05 times 10 to the power minus 10 Newton. Now, once you find F net, of course, you know what is the acceleration of the electron, but you need the mass of the electron. Mass of an electron is equal to 9.1 times 10 to the power minus 31 kilogram. This will be given. Usually is given. So now you say, according to Newton's second law, F net equal ma, and a is unknown. F net known, mass is known. You find a, which is 1.15 times 10 to the power 20 meter per second squared. It's a very high acceleration because the particle is small, so it accelerates at high. So here I'll show you the detailed answer on another piece of paper. This is the detailed one with the calculations and everything. Hi. Now we'll do question 27 from the practice sheet of chapter 21, electric field. This question says we have a uniformly charged rod, has a length of 2 meters. It's a rod with a length of 2 meters, and its charged per unit length, lambda, is 3 nanocoulomb per meter. So this is the linear distribution of charge, 3 nanocoulomb per meter. Now what happens to the rod? We bent it to a semicircle. So we made it as a half circle, semicircle. Now the question is, what's the magnitude of the electric field at the center here due to the distribution of charge here? From here to there you have positive charge. What's the effect of the total charge here at the center? Now, one of the things we have to pay attention to when we have distribution of charges, we look at symmetry, because symmetry can help us to eliminate some of the electric field component whenever, of course, we have a symmetry. Here you can see there is a symmetry because the x-axis is the symmetry axis, which means any point here in the first quadrant has a point corresponding to it on the fourth quadrant. So here, 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 and here, mirror image of the points. So this will help us in solving the electric field in an easy way. So symmetry, it's one of the things you have to pay attention to. Now let's look at the steps how to find the symmetry of the electric field. So what we have here, we have the rod, which is 2 meters. We bent it, this is 2 meters, bent it to a semicircle, half a circle. So the arc S, same as the length L. So the length of this arc S is 2 meters, because it's the same. And remember, this is half a circle. So from the formula of circumference is C is 2 pi multiplied by the radius. That's the formula for circumference of a circle. Because here we don't have a circle, we have half a circle. So what we'll do, we divide both sides by 2. So this will give me half a circle circumference. And R small is the R capital here. When you take half of it, pi R, this half of the circumference, and remember half of the circumference is L, and L is 2 meters. So from here I can find that the radius of this semicircle is 2 over pi, and pi is 314. Now, to find the electric field, remember electric field is a vector. So what we do when we have distribution of charges, we take an element of charge, which represents the whole charge. Let's take an element of charge here. And this element of charge is not the total Q, it's part of the Q. So here we'll have dq. Now what does this dq do at this point? It has an electric field. This is positive charge. So imagine there is a test charge here. What happens? It will be repelled this way. So the electric field will be this way. Now remember we have symmetry. So this dq, it has a mirror image here. Here we are not taking 2 samples. just to show you the symmetry. There is a dq here, image of that. Now the effect of this one here is this way. This is the electric field of this charge. Of course, this is not the total, so we call it dE. The electric field of this element is this way. Now, what about this element which is symmetrical? What's the electric field here? Of course, this is the same R, and this is positive, test charge positive, so you have an electric field this way. Again, for this sample, dE. So what we noticed here, that whenever you take an element, there is another element which has an electric field, same magnitude, but in the other quadrant on the symmetry axis X. Now, according to this, now whenever I take any electric, now let's concentrate on this one, dq. So dq here, it gives me dE, and this dE has component. It has dEx, dEy element. This is for this element. But what about this element dq? It has dE this way. So suppose this is number 1, this is number 2, this is dE number 1, this is dE number 2. Again, this dE, it gives you dEx, dEy. So in total, you can see that whenever you take an element, the electric field on y-axis, they are always opposite to their mirrors. If you take one here, you have another one here. You take one here, you have another one here. So in general, you'll find that dEy, they're always opposite, and you have many of them, and they cancel each other. So here, what we say, dEy equals 0, which means the total Ey equals 0. This is for one element, but for all the elements, 0. But the dEx for each element, you can see they always add up in the same direction. So it means dEx is not 0, it's the total, and it's dE net for all the samples. Which means now the symmetry helps us to say that there is no electric field on Y, only on X, and we just have to calculate the electric field on X. Remember, dEx means the X component, and the X component, if you look here, if you say for this element, as example, this angle is theta, you find this is theta. And even for this one, if you say this is theta, for this element, it's theta. So theta with X, which means dEx is d cosine theta. So you have dEx, it's dE, the element, multiplied by cosine the angle theta. Theta here is not constant, because of the element here, theta is small, here it's larger, and theta changes. Now, what's the smallest theta? If you just think of half of the circle here, smallest theta is 0 here, and then start increasing to 90. That covers half of the circle. Of course, you start here, then you go to minus 90. So your angle changes from minus 90 to plus 90. Right. Now, how do we find the electric field of a point? This is like a point charge. What's the electric field here? One element, dE is K. The charge here, the point charge, is dQ over R square, which are the distance between these 2 points, and the same. This is the same as the radius. Yeah. Right. This is dE, only dE, but our total is dEx, so we have to substitute here. So DE net, which is DEX only, which is DE cosine theta, can be written as DE is this one, K DQ R square cosine theta. Again, I remind you here we're talking about magnitudes only, no direction. DE net. Now in this equation you can see that we have two variables if we want to do integration, because the charge, yeah, is not the total charge, so that's a variable, and the angle is not constant. For each element there is a different angle theta. So two variables, which means if you want to integrate both sides, this will give you the electric field total, but here you can't integrate until you get rid of one of the variables. How we get rid of one of the variables? Let's see the connection. First we have lambda. Lambda is constant, linear, so we try to write dq in terms of lambda. Remember that lambda we defined as total charge over total length, and if it's uniform, lambda is a sample of charge, sample of length, dl. Okay. Now in this case we are not talking about the road, we're talking about the arc. So L here is an S, so lambda is dq over ds, which means I can replace dq with lambda ds. So dq is equal to lambda ds. So now I can replace this one with lambda ds, which means I have k lambda ds over r square cosine theta. Still I have two variables. I have s, now s, the arc of course changes, and theta. We have to unify those two, one variable. Now we go back to the definitions of theta for for the arc. Remember in radian, if theta in radian, rad, it's equal to the arc length s over the radius r. So theta is s over r in general. So if you take s here, what you say? You say s equal r theta. Now when s changes, theta will change. R is constant, so these are the two variables. If we differentiate both sides, you'll have ds, r is constant, d theta. So I can replace ds with r, d theta here. So we'll have k lambda r d theta over r squared multiplied by cosine theta. You can see that one r cancels out, so we'll end up with k lambda over r. I rearrange, I put d theta on the front, cosine theta d theta, integration e net. Now you can see here k constant, lambda constant, the radius is constant for any element, the distance is the same to the center, so the only variable is theta, which means we have to integrate this one. Now when you integrate theta, what is the smallest theta we have? This element start here, so the smallest is minus 90 and the largest is plus 90. Your angle changes from here to there. What I can do, I can say from 0 to 90, but I multiply the integration by 2, it gives me the total. Or you say from minus 90 to plus 90, it doesn't matter. So here we say this is k lambda over r, integration from 0 to pi over 2, but we multiply this one by 2. The 2 is for angle, cosine theta d theta. Now the integration of cosine theta d theta is sine theta. So we'll have 2k lambda over r sine theta, and the limit from 0 to pi over 2. Now the integration here is finished. I can substitute upper sine 90 is 1, lower sine 0 is 0, so we'll end up with 2 pi lambda over r. So we'll have 2k lambda over r sine 90 minus sine 0, and this will give us 2k lambda over r. This is 1 minus 0, which means the integration is 2k lambda over r. Now k is known, lambda is known, r is unknown. How do we find r? Of course, r, we found it from here. It's 2 over pi. So replace r by 2 over pi, substitute, you get the total e. So if I take this one up here, what I'll find, that e net total equal 2k lambda over the r, we replace it with 2 over pi, 2 with 2 cancels, k lambda pi, k known, lambda known, and pi known. So when you substitute all these values, you get the value E equal 84.8 Newton per coulomb. Okay, so a couple of things here regarding these questions. When you have an arc, first look for symmetry. If it's a semicircle, of course you have symmetry. If it's a complete circle, of course you have symmetry in all directions. So you'll find that E here is 0. If it's a complete distribution on a circle. If it's a quarter of circle, there is no symmetry. So when it's a quarter, you just have E, then you'll have two components, EX and EY, and you have to calculate EX and EY, then you find E total. So be careful when you don't have symmetry. What if you have 3/4 up to here? Remember, if you have semi, you just have on X only. And a quarter, no, you have X and Y. So at the end you have X and Y. I'll show you the final answers in detail here. But just pay attention to the last part. This is the solutions in detail. Well, just look here. I did the integration from 0 to 90 pi. Okay, and then once I finish this, I multiplied it by 2 to say from minus 90 to plus 90. This 2 is for double. And then I replace the radius by 2 over pi. Right. Now let's look at question 29 from the practice sheet of electric field, chapter 21. Question 29 says, in the figure, here, this figure, we have a ring. And the ring has a radius of 0.71 meter. So the radius of the ring is known. And this ring carries a positive charge, but this is not the charge, positive charge, sorry. This is positive charge, and the charge, total charge of the ring is 580 nanocoulomb. This is the total charge of the ring. And it's uniformly distributed, which means the distribution is uniform. There is no one side has higher charge than other or any point has charge more than other point on the ring. Now we have a point charge capital Q and is placed at the center of the ring. So here we put a point charge capital Q at the center. The question says the electric field is equal to 0 at point P, here at this point on the axis of the ring. The electric field here is 0 at point P, which is on the axis of the ring, and it's 0.73 meters from the center. So the distance from here to there is 0.73 meters. Now the question is, what is the value of the point charge Q? What's the value of Q here? Now the electric field total at P is 0. And what's the charge? Q, capital, the point charge here. But the charge of the ring is known, 580, and it's positive. Now you remember from previous study, we found the electric field of a distributed charge on a ring at a point away from the center on the axis of the ring. So we have the formula for the electric field for the ring only at point P. Now the question says the electric field here total is 0. Why is it 0? Because here we have two charges. We have the ring charge, it has an electric field, and the Q has an electric field as well. Now how do we make the electric field here equal to 0? Remember, when you want electric field to be 0, it means the electric field of both must be equal. So if we say that the electric field of the ring is equal to the electric field of the point charge Q, but opposite, of course, then they cancel each other at this distance x. So the idea here is to say that the electric field of the ring equal in magnitude to the electric field of the point charge, but opposite here. Now if this is positive and you put a positive test charge here, of course it will be repulsion, but on xy. So the total for the ring will be on the x-axis. Remember, because of the symmetry of the ring, the total electric field, if you go back and look at the electric field of a ring, the total electric field of a ring is always on the x-axis, central, because the y-axis, they cancel each other because of symmetry. So the total of the ring is here will be on the positive x-axis this way. Now Q, if Q is positive, then it will add up because there will be repulsion as well. But here you have to assume that Q is negative charge. So you have attraction this way. Then they'll be opposite. But anyway, we need the magnitude to be equal. Magnitude of the electric field of Q point charge and the ring. We just have to equalize these electric fields and we solve for x. Then it tells us at what point I have to put the Q and what's the value. So let's do it here. Now we say that the electric field of the ring, change the pen, only for the ring, it's positive. The electric field here at an x position, the total will be on the x-axis. This is E of the ring only, this way. If you put a positive charge here, test charge, and all these positive, okay. So the total will be on the x-axis, because the y-axis, because of symmetry, they cancel each other. Now this is empty. Now what if I put a Q capital here? because the question says what's the value of a Q which you have to put here. So you have the total electric field here 0. So I have to put a charge here, Q capital, and it must be negative. So I have electric field of the Q this way. So I'll assume it's negative. Then I'll have E of Q this way, and then I have two electric field opposite. Now, if the electric field total is 0, I want it to be 0 at point P, then I must have this electric field equal to this in magnitude. So we say E of the ring must equal E of the charge. Now, E for a ring, as I said, you don't have to do the calculations because we already did it. If you go back to the theory, you find that's equal to K, X distance from the center to the point, the total charge of the ring, Q ring, I'll write it small to remember this is the Q of the ring, total for the ring, Q small, divided by the radius of the ring square, so if you call it capital R, plus distance from the center to the point square, all raised to power 3 over 2. And this is the electric field of a ring at a point on the axis. This must equal the electric field of this point charge. For a point charge, it's easy to find the electric field. It's just K, the charge. I don't need the sign because I need the value. The charge is a Q, and the distance here R square, but R square here is X square, so it's X square, and you can see it's the same. Now we can cancel K and put the values. Q is known. This is the value of Q ring. X is known. Radius is known. So, and Q is unknown. Remember, you want the charge Q. What's the value of Q? You put at the center. So the only unknown is Q. Everything else is known. So when you put the values, you find that Q is 2.113 times 10 to the power minus 7 coulomb. You can change it to nano coulomb. So you need a minus 9 here. This will increase by 2. So 213 times 10 to the power minus 9 coulomb. And it's 2.213 nano coulomb. This is the value of the charge. So remember, the electric field of the ring is known at a point here. It's found in the previous theory. Here you have the detailed solution. The question. Now this is a question 30 from the practice problem of chapter 21, electric field. What we have in this question says, consider there is a linear uniform distribution of charge as shown here. So you can see we have distribution of charge starting from 0 to 270 degrees. It's 3/4 of a circle. What's so special about this distribution of charge is that from 0 to 180 is positive, charge is positive, but from 180 to 270 is negative. So here we have half a circle positive and 1/4 of a circle negative. The question is, determine the direction of the electric field at origin, not the magnitude, because we don't have values here, just the direction, which means what's the total electric field here because of the both distribution. And to find the total here, of course, you have to look at the vectors effects for the positive and negative, and then you find the final direction of the electric field. So E net here, the direction only. So the choice is, would it be in the first quadrant, the total, second, third, fourth? Which quadrant you'll have the total electric field direction? What we should do in this question, if you remember, we did previously a question regarding a semicircle. So if I see the effect of the semicircle at the center, which way is the electric field? Total, of course, the net for the electric field of the semicircle. I draw that one. And then I draw the electric field effects of the negative, the arc here at the center. So I'll have two vectors, vector for the positive, vector for the negative. I draw them and I find the total or the final direction from the drawing. So let's look at it this way. I did a solution here, do a sketch. Now I'll divide the question to the semicircle positive only. This is the semicircle, and this is the center of the circle. Now, which way is the electric field total of this distribution? If you remember, if you take an element, we said, and you find the electric field here, this is positive, a test charge, so the electric field is this way for this element, dE. But because of symmetry, you have another element here, and its effect dE this way. So at the end, because of the symmetry here, but here the symmetry is on Y, the previous question was on X, but it doesn't matter. So when you look at any electric field effect of any dQ here, you find that it has another dQ here, gives you the same electric field on the other side, which means now if I take the component of this dE, you have dEy, dEx for this point charge or for this element. But this element has this dE, so it has dEx, dEy. Now because of this symmetry, it means dEx always they are opposite for any elements, which means the total for X is 0. So what is left? The total is in Y. So for the semicircle, the total electric field of the semicircle, which is positive, is dy, is down. So I can draw it here. This is the center. This is the total E for the positive, because they all add up on Y. Now we come to the negative, this part. What's the effect here? If I take a sample here, dQ, at this distance r, dQ, this is negative, this is, put a test charge, positive. So which way is the electric field here? Attraction, so you have E for the negative this way. Here we don't have symmetry, so it means E for any point charge here is always in the third quadrant. So if you take another sample here, which means E has X and Y. This is dE small, negative. You have dEx negative, dEx, dEy negative. Which means here we have no symmetry, and the total E here for the negative is always in the third quadrant. So it's somewhere here, dE. So this is E total negative. Now what's the total of both now together? It means what's the total of these two vectors? If you have vector in the third quadrant and vector on the y-axis negative, the total will be in between them. So if I complete this, this is the total E net. This is the negative electric field direction. This is the positive electric field direction. This is E positive. This is E negative, and the total is in between. So the answer is in the third quadrant. The total electric field will be in the third quadrant. The direction, the third quadrant. Okay. You have the solutions. Of course, I did it before. Okay. It's in the sheet provided. Okay. So the positive will give you total on Y. The X will cancel. The negative will give you a total in the third quadrant. So you have third and Y. So it's in the third. Right, we'll do now question 33, practice problem on electric field, chapter 21. Here we have a 16 nanocoulomb charge is distributed uniformly along the x-axis from x equals 0, from here, starting the charge from here, to x equals 4. So from here to there, we have a distribution of charge on a line, linear distribution, but the total charge is 16 nanocoulomb from 0 to 4. Now, which of the following integrals is correct for the magnitude of the electric field, only magnitude of the electric field, at position x equal plus 10 meters on the x-axis? So it means what's the total electric field at point P here, which is 10 meters from the 0, 0. Right, here we have linear distribution of charge. And to find the total electric field at P, the question here, we have to take a sample and we consider that sample as a point charge. We find the electric field of that sample and we try to minimize the integration to one variable based on the parameters given in the question. Okay, so let's see if we can do this one now. What do we have here? The total charge is 16 nanocoulomb, and the charge starts from 0 to x equal 4. So from here to there, x 4 meters, and the charge is positive from here to there. Now, what's the electric field total at P? And P is 10 meters from 0, 0. From here to there is 10 meters. What's the total electric field here? To find the total electric field here, we take a sample of charge, a point charge. We call it dq to represent the total. And we find the electric field of this point charge here. Now this is positive. You put a test charge here positive, so it's repulsion, which means the electric field of this point charge, dE, not E total, dE sample, this way. Here we are not interested in the direction, just the magnitude of E. Of course, we take another sample here, you still get the same dE this way. Everywhere, E is on the positive x-axis. Now, to find the total effect of the charge, of course, the charge here has stronger electric field at this point. The charge here is far away, so it has less. Here is medium. So what's the overall effects here? For this point charge, the electric field is dE for the sample charge, K, the sample dQ, the point charge, over R squared. And remember, R is the distance from the point charge to the point. So from here to there, we call it R. Always R is the distance between the charge or the point charge to the point. Now, if I want total E, I have to do integration of both sides. The dE becomes E net. here I have to integrate here, of course. K is constant, so no problem. dq, a sample, this is a variable because the charge is not dq, it's total q from here to there. And r as well is variable from here to there. This is for this point charge. If the point charge is here, or the sample charge is here, you have a different r. So r is changing. Here we have two variables. So when you have two variables, you have to minimize them to one variable to do integration. Now, because we have linear distribution, so lambda, the linear distribution of charge, it's always equal to the total charge over total length. Charge over length. Now, here, because we have sample of charge, so lambda is sample of charge over the length it takes, dl. So this dq has a distribution on this length, dl. This is total L. But since L is on X, so we don't want to create another variable L. L is on X. So we change it to lambda equal dq over dx. dl here is dx. So dq then is equal to lambda dx. Multiply this, lambda dx. Okay. Lambda dx. So replace dq here with lambda dx. So you have k lambda dx r square. Again, now dx, x is variable from 0 to x to p. And r as well is variable, so I still have two variables. Now we have to link these two variables to come up with one variable. Now what's the link between x and r? Of course, r here is not x, because x is always the distance from 0 to something. So for the point charge, from 0 to the point charge, it's x, because the charge is changing from 0 to 4. So x is the variable here, from 0 to the point charge. And from the point charge to the point, that's always r. And in this question, I know from 0 to the point is 10. So I can put or write r in terms of x and 10. So 10 total minus x gives you r, or r plus x is 10. So r is 10 minus x. Now I can replace r square with 10 minus x square. So 10 minus x is r square. Now you can see here, the only variable I have is x, which means I have to integrate now on x. Now x here to do with the charge. Where is the starting charge? At what point? Start at x0 in this question. So x initial is 0. Where it finishes, the charge finishes at 4. So x final is 4. So this is my integration. Now if you want to compare it to the answers, of course, the value of k is known. Lambda value here is not given, but what is given? The total charge. And of course the total length as well is given. So I can find lambda using this equation. So I say lambda q total over L. And q total is 16 nano times 10 to the power minus 9. The length of the charge from 0 to 4, so it's 4. 16 over 4 is 4. This is lambda. This is coulomb per meter. Now if I substitute here, we get E net equal K 9 times 10 to the power 9, that's the K. Lambda is 4 times 10 to minus 9. Integration dx over 10 minus x square minus plus 9 times 4, 36. Integration dx 10 minus x square from 0 to 4. Of course here from 0 to 4. And you can tell this is the choice which you are looking for. Okay. And I gave you the solutions before on a sheet. So this is the detailed solution of the question 33. We took a sample R. This is x from 0 to the sample. This is dx and dq at the same time. This is 10. Same steps. This is the answer 36 from 0 to 4 dx. Right, we'll do now question 34 in chapter 21, electric field, from the practice problem sheet. Now this question says there is a uniform linear charge of 2 nanocoulomb per meter. So this is the distribution of charge, lambda. It's on a line. It's distributed along the x-axis. Can you see? It's on the x-axis. And the distribution starts from x equal to 0, yeah, to x equal 3 meters. So from here to there is 3 meters, and from here to there we have a charge distribution. Of course, the charge distribution here is positive charge because it says 2 plus 2. Now the question is, which of the following integral is correct? Which of them is correct for the y component of the electric field? For the y component of the electric field, not the total electric field, just a component on the y-axis of the electric field, where at point y equal 4 meters on the y-axis. So this time we don't want the electric field along the x-axis, no, it's on the y-axis. What's the electric field here at point P, which is 4 meters from the wire? And this is 0, 4 meters, so 0.4, y equal 4, and x equals 0, of course, at point P. So how much is the electric field? Not the total, only the y-axis, y component of the electric field here. So here we have from here to there 3 meters, the charge distribution. From 0, 0 to this point is 4 meters. Okay, let's start looking at the solution, how to solve it. Right, so the first thing is that we know lambda, and we know it's the distribution of charge from 0 to 3. So this is 0, this is x equal 3 meters. So it means from here to there, it's 3 meters. And from here to there, the y-axis is 4 meters. So from here to there, 4 meters. So how much is the total electric field here? Now, of course, let's take an element as usual. I take an element somewhere here. And in this element there is a charge dq, a point charge like. We have to find the electric field of this point charge here. Now where is this dq? Of course this is 0. From 0 to the to the sample, we said always we call it x. And this charged element has a length of dx, which we usually say dl, but it's on the length of dx. That's the length of it, which it takes. Now, if this is positive, remember here, if we assume there's a positive charge, test charge here, what we have on the line of action, yeah, this is the line of action, we'll have repulsion, so we'll have electric field of this element only. It's a DE sample. So we can see here DE, if we have X and Y here, you see D is in the second quadrant, so it has two components. It has DEX and it has DEY. Now the question says find the y component only, so ignore this one. We don't want the total. When you want the total, you need both. Right, so here the question is, how much is the EY? Right, if I look at the magnitude, of course, yeah, EY, I say is K dq over r squared. And where is r squared? This is r from here to there, r squared, the magnitude. Now, as usual, we have two variables, and if I want to do the integration, because here if I want EY, I have to integrate this one. Integration of the point charge, which gives you the total charge. Now let's see what's the connections between r and x and the other variable. And dq, as usual, remember we get it from lambda. Lambda is total charge, q total over total length, or sample of charge over sample of length. Here my sample of length, instead of calling dl, I call it dx. So dq will be lambda dx. I can replace dq with this. Now I have r. I have to write it in terms of x. Now we can see here we have a triangle. So in this triangle we have r, x, and this is fixed for the x is variable. So we say that r square is equal to 4 square plus x square, and 4 square is 16 plus x square. This is r square equal to, and here we need r square, not r, so this is enough. We don't have to take the radical. So r square now can be replaced and dq replaced. So we'll have the component of the electric field on y. Okay. Just forgot here to tell you that EY, dEY is dE sine theta. We need the angle, of course. So if I assume this is theta here, this will be theta as well. So this dy will be d sine theta, and of course sine the angle with x. So if I want EY, I have to integrate dE sine theta, and dE, we said this is dE only. So we'll have k dq over r square sine theta. Now in this case I have three things I have to unify. The theta, of course, is linked to the x and 4. We don't want r, so sine theta equal what? Sine theta is 4 over r, but r is not relevant for the calculation. We need r in terms of x. So if you go back here, what is r? R will be 16 plus x squared to power half, the radical. So now I replace sine theta and r square and dq in terms of the other things here. So I have EY equal k, the dq we said is lambda dx, the r square is 16 plus x square, and the sine theta, we look here, what is sine theta now? 4 over r, which is 16 plus x squared to power half. Now replace sine theta by this term, 4 over 16 plus x squared to power half. Now here you see it's the same term. This is power 1, this is power half, so it's power 16 plus x squared to power 1.5, 3 over 2. K lambda dx integration. This will give us EY only. Now we need the limit. Here we're integrating in terms of x. Lambda is constant, k is constant. So what's the smallest x for the charge is 0. The largest is 3. So it's from 0 to 3. Now to compare with the integrals given, the choices, you just have to substitute. K is 9 times 10 to the power 9. Lambda is constant known, is 2 nano minus 9 dx over 16 plus x squared to the power 3 over 2 integration. Minus 9 plus 9, 9 by 2. And here, don't forget we have a 4 here, we missed it. We need it here as well. So we need the 4 here. 4 multiplied. So we have 4 by 9 by 2, which is 72. So we'll have 72 from 0 to 3, this is 0 to 3, dx 16 plus x squared to 3 over 2. So this will give us the choice B. The answer is B, the second one. Sorry, not B. The answer is A. A is 72 dx over 16 plus x squared all to power 1.5 from 0 to 3. So this is the answer for the electric field on y-axis. Of course, if we want the total electric field, no, we have to calculate dEx as well. And dEx is dE cosine theta. So the difference will be that here, you write dE cosine theta, and cosine theta, you have to find cosine theta, which is x over r, but you have to write it in terms of the other units. That's if you have the value. Then you do square of the x component, square of the y component, and the radical gives you the total electric field at point P. Okay, you have the solution, of course, for this one on the solutions of the sheet. I'll show you the final answer here. Question 34. Okay. So now let's do question 36 from the practice problem sheet of chapter 21, electric field. What we have here, we have a particle. It has a charge Q, positive charge, and it's 3 millicoulomb, 3 millicoulomb. And the mass of the charge is 20 grams. Okay, that's the mass of the charge. So here is not an electron or a proton, no, it's just a bigger thing. You have a charge on a mass. Okay? And this particle has a speed of 20 meters per second. So initially the particle going at this speed, 20 meters per second. Now, this initial velocity of the particle, when it enters a region where the electric field has a constant magnitude of 80 Newton per coulomb. This is how strong is the electric field. And it's constant, it's not variable, so everywhere is the same value. And this charge Q enters this electric field, but how it enters, in what direction, and a direction which is the same as the velocity of the particle. So the direction of the velocity, the direction of motion of the particle, and the direction of the electric field are the same. Now, of course, when it enters, the particle enters the electric field will have an effect with the charge positive here, and because it's going in the same direction, of course it will accelerate it. If it enters then the opposite direction and it's positive charge, it will slow down. But here it says going in the same direction of the velocity, the direction of the electric field. So once it enters this electric field, which is in the same direction, what happens to the speed? Will it stay at 20? No. Higher? Yes, because it's in the same direction. So after 3 seconds, we need the final velocity or final speed. So this is the question. Let's do a sketch and see how we can solve this one. So here, let's say we have an electric field going from left to right this way, and it's constant, the electric field. So when it's going from left to right, it means you assume that this side is positive, source which gives you this electric field, going to somewhere far away negative. Now the particle Q will go inside this field, but it's not like vertically, no, it goes in the same direction of E. So initially it's here, the Q, and it has a velocity in the same direction of the electric field, E. So the initial velocity, VI, here, known, 20 meters per second. Now because this is a positive charge, can you see here, you have positive, positive, so it will repel it, which means it will accelerate. So when it's here, after 3 seconds, from here to there, we have 3 seconds, of course you'll have a different velocity, final velocity. The particle will have a different velocity, Q final. How much is this final velocity? V. The V final, unknown. The V initial known, and the time is known, and the electric field is known. Okay. Now, when the electric field is constant, it means the electric force will be constant as well. So, what's the link between electric field and electric force? We know that the electric field E equal to electric force over the charge Q. And the electric force here is the only force. So here the electric force is the F net, total force on the particle. And F net, Newton's second law, tells us it's the mass of the charge multiplied by its acceleration A. Remember, when you deal with velocities, initial velocity, final velocity, time, you need the acceleration to use the equations of motion. So what we'll do here, E known, okay, Q of course known, we can find the F net. And if we know F net and we know the mass of the charge, it's given here, I can find the acceleration. And if I find the acceleration, I can use the equations of motion to find the final velocity. So the next step is this. Either I break it to pieces or just join them. So I can say down here without calculating, what is E equal to in terms of M and A? Fe is F net, and F net is Ma. So we replace it with Ma over Q. So from here I can say the electric field is equal to QE over N. Q known, 3 times 10 to the power minus 3 is milli. The electric field E, which is constant 80, over the mass of the particle 20 gram, or 20 times 10 to the power minus 3 to change it to kilogram, of course. Yeah. Now from here you find the electric, you find the acceleration. Once you find the acceleration, this calculation, you can apply equations of motion. Since we have the time, initial velocity, and we want final velocity, the easiest equation is the first equation of motion. Final velocity equal initial velocity plus acceleration multiplied by time. Final velocity unknown, initial velocity known, of the particle 20. Acceleration is this, so I just put it as it is. 3 times 10 to the power minus 3 times 80 over 20 times 10 to the power minus 3. This is the acceleration, and the time is 3 seconds. So everything is known except V final, and we find V final is 20 plus 36, which is 56 meters per second. So this is the final velocity of the particle. Of course, you can see it's higher than the initial. Initial is 20, final is 56. It's accelerating. It's speeding up because it's going in the same direction of the electric field. Now we'll solve practice problem question 37 from chapter 21, electric field. Now in this question, what we have a particle which has a charge of 4 millicoulomb and a mass of 50 grams. This charge has a velocity of 25 meters per second, and it's moving in which direction? In the positive x direction, so it's going on the x-axis, positive x, this way to the right. Now, if no electric field there, of course the charge will continue on a straight line at the same velocity. But what happened here? While it's moving, it encounters first enters a region where the electric field, there's an electric field, is uniform, which means constant, and the value is 60 Newton per coulomb. And this electric field this time is directed in the positive y direction. So it's going from the bottom to the top, the direction of the electric field, up the y direction, which means the angle between the velocity entrance and the electric field is 90 here, perpendicular. Now the question is, what's the speed of the particle 5 seconds later after entering the region of this region when it's inside the electric field? Of course, here you have to pay attention to a couple of things here. When the charge enters the electric field, so initially when the charge is here, it's just as if it's going straight on the positive x-axis. But because you have a charge and the charge is positive and you have an electric field pointing up, there will be a deflection. The particle will not go straight, it will be deflected up. But because it has velocity, so it will not be deflected straight up, so it will create a path similar to a projectile, an arc. Yeah. So let's see how we tackle this problem and solve it. This is what we're gonna do here. So the charge is known, Q, positive here, going in the positive direction of x-axis. This is the x-axis, this is the y-axis. So here the velocity is 25, here is 25 meters per second. That's 25 here, sorry. So this is 25 meters per second. Okay. So what's this inside the electric field? Remember, if the E is directed upward, it means here we, as if the source is positive charge and here the top is negative charge. So positive, there'll be a repulsion. If the charge is at rest, it will be repelled and it moves in the direction of the electric field straight away. But because it has a velocity on the x-axis, it will be deflected following a projectile path, an arc. So slowly it bends and moves on an arc. So this question is like motion in 2 dimensions and similar to a projectile motion which you studied in physics 1 mechanics. So how do we solve this problem? Remember here the electric field is constant, we have 60, and time taken from here initially and here finally, from here to there we have 5 seconds. Initial velocity is known, 25. What is the final velocity and final speed? Of course, once you know the velocity, you can find the speed, which is the magnitude. To find the V final velocity, remember velocity is a vector because it's 2 dimension. You have V final on X, which is I, plus V final on Y, which is the J component, 2 components, Vx and Vy. So I have to find Vx and Vy. Now, on the x-axis, there is no acceleration because there is no force, nothing on the x-axis. So it means the initial velocity x and final velocity x are the same. If you remember projectile motion, we said Vx, the component in x here, is similar to V naught x, the initial velocity here, V naught x, or Vix, same. And V naught x here is V naught cosine theta. Now what do we mean by theta? Theta is the angle, and here the angle of entrance is 0. So it's like you are throwing a stone horizontally, so initial firing angle is 0. But the only difference here, like similar to gravity, but here it's like the gravity is this way, not downwards. So the arc is up, not down. You can always turn the page upside down, and then it looks like you threw something horizontally. So here theta is 0, initial, of course, theta naught, initial firing angle 0. Okay, so it means Vx here and Vx here are the same. So Vx equal V naught x, which is here I put V naught, but V naught, remember, is V initial is known, 25, cosine 0, which is 1, so it's 25. So now we found the Vx final. This is Vx final is known. What is left is Vy final, the y component here. So to find Vy on the y-axis here, we have acceleration. So Vy here and Vy here are not the same. Of course, here V naught y is 0 because the angle was 0. And because the electric field is constant, so the electric force is constant. And if the electric force is constant, the acceleration is constant. And then we can use the equations of motion. Because we have time, so here we're talking about the y component only, the y. This is the x component. So Vy final, Vy final, equal V naught y, initial here, plus the acceleration multiplied by the time taken between these 2 points. V naught y is V naught sine theta naught plus AT Vy. Theta, we said, is 0, so sine 0 equals 0, so this terms equal to 0. Now what is left? Vy equal acceleration multiplied by time. Now the time is known, but the acceleration is unknown. So how do we find the acceleration? From Newton's second law from the electric field. If we go back like what we did before, the electric field equal the electric force over the charge. And the electric force is, according to Newton's second law, is the mass of the charge multiplied by acceleration over Q. So if you want E, rearranging this gives you the acceleration equal to QE over M. This is always true in electric, QE over M. So we replace it by charge, electric field over mass, multiplied by the time. This is Vy, the component of the velocity. Now here everything is known, Q known, E known, time, and the mass. You just have to substitute. The charge is 4 milli, so minus 3. Electric field 60. The time 5 seconds. The mass 50 grams, so change it to kilogram. And then you find Vy, which is 24 meter per second. This is Vy here, the component. Remember, V final is in this direction here for the charge. It has two components. It has Vx and Vy. Vx we said same as V naught x, 25. So we found Vx, 25. Vy here we found it equal to 24. So how much is V final as a value, of course, as a speed or value, equal to Vx squared plus Vy squared. Vx squared 25 squared plus Vy squared 24 squared, and gives you the value 34.65 meter per second. This is the final speed. So what you learn from this question is that the path of the particle inside an electric field, when it enters at 90 degree, when I say 90 degree, I don't mean the angle of entering, the angle of firing, no. The angle between the velocity and the electric field is 90, perpendicular. Then the charge will take a path similar to a projectile. And here the projectile initially is like it's being fired horizontally, so the angle of firing theta naught is 0. And start bending. Once it reaches here after 5 seconds, the velocity will be pointing this way, tangent to the path. So it has two components, Vx and Vy. You have to know Vx and Vy. Vx for projectile motion is constant because there is no acceleration on x. Remember, acceleration in x is always 0, no acceleration on x. So it's 25, same. V here, same, Vx. But Vy will change. Here is 0, V naught y, and slowly it develops Vy, and here it increases. So this is the Vy, 24, and you find it. So this is how you solve it. You have the solution given to you in advance, and this is the solution here, 37. Alright, now we'll do question 40 on chapter 21, electric field practice problem. In this question, what do we have? A point charge, a charge which has a mass of 1 gram, and this charge is attached to the end of an insulating cord which has a length of 55 centimeters. And is observed to be in equilibrium. This charge is in equilibrium, which means it's not moving, in a uniform horizontal electric field of 12,000 Newton per Coulomb. So when we have this charge inside an electric field of this value, it's not moving anymore. Of course, the charge will move inside an electric field unless there are other forces preventing it from moving. So now the charge, it reaches a state of equilibrium. Why is that? Let's see. So there's an electric field of that value. When the pendulum's position, this is a pendulum like, is as shown in the figure here. So when we have this arrangement, this is the charge. We have an electric field going from left to right, okay? And it affects the charge which is hanging on a string or a cord. So you see that there will be an electric force affecting that, and either push it or pull it, depends on the sign of the charge. As shown in the figure, with a charge 12 centimeters above the lowest vertical position. Now when you have it here hanging, this is the lowest, when you put the electric field on, because of the effect of the electric field, this charge will move to this position, so it goes up from the lowest by 12 centimeters, this high, 12 centimeters. Now if the field points to the right, it's drawn here to the right, as in the figure, determine the magnitude and the sign of what? Of the charge, a point charge. So it means what's the value of a Q? Q capital or Q small, it doesn't matter. Find the value of the charge and its sign. So we want to find Q, the charge, Q. Now let's look at the steps to solve this question. Now here I did a diagram for you. Initially we have a pendulum, a cord with a length L, and L is 55 centimeter. Now you put a charge at the top, at the end here. Okay. Now if there is no electric field, of course it stays in this position. Now when you apply an electric field this way, from left to right, so it means this side is positive, that side is negative, this charge will interact with it. Now according to this arrangement, what's the sign of the charge here? Capital Q. The sign of the charge, capital Q. What it should be, the charge, positive or negative to reach here. Of course, if this is positive, this must be positive, so to repel it to reach to this point. So now the first part, we know the sign of the charge is positive. Now once there's a repulsion, the pendulum will move up and it creates an angle theta. Of course it will not go forever up, it reaches a point and stops, and that's when we have the equilibrium, which means the particle is not moving anymore, it stays here. Now why it stays here? Because there are other forces will balance the effect of the electric field. So at the moment we have this arrangement. It is from here to there is the length 55 centimeter, which is the same as this length from here to there is 55 centimeter as well. These are 55 the total. And the charge went up vertically by an amount y, which is 12 centimeter or 0.12 meter. Right. When the charge is here at equilibrium, it means the forces are equal on both sides. So let's see what are the forces we have in the charge. First, the electric field has an electric force effective. So if I want to draw, this is the charge Q here. What are the forces? First we have a repulsion force this way. So this way we have a repulsion force. I call it F electric, Fe, force of the electric field, repulsion. That's the force which push it up and then stop here. What else do we have? We have a cable here, tension, cord. So we have F tension. And this charge is not just like a normal charge. It's on a mass, so it has a mass, which means it has a weight. So there's a force of gravity Fg. So according to this arrangement, we have three forces. We have the electric force, repulsion. We have the tension force this way, and we have the force of gravity down. Now the only force which has component is the tension force, but those two forces are not, so I can put its component this way and this way for the tension force. Now if this angle is theta, like it means if I look at it here, it means the angle with y is theta this time, same angle, alternating. So it means this component will be ft sine theta, not cosine theta, because the angle with y. And here we have ft cosine theta because the angle theta is with the y-axis. Then we can cancel ft. So now what we have forces to the right, forces to the left, we have forces up, forces down, and this object is not moving anymore, the charge. So equilibrium. Equilibrium means there is no acceleration, no motion. So forces to the right equal forces to the left in magnitude, forces up equal forces down. So we'll do that and to see what we can get out of this. So for the x-axis, I say electric force equal tension force sine theta. This is the electric force, this is the tension force. They are equal. Up and down is equation number 1. Forces up equal forces down. I'll put the sine and cosine on one side. So I'll put Fg down equal F tension cosine theta up. This is equation number 2. You can see here we have sine and cosine, so the best thing is to do to divide these two equations. So I divide this one over this. I have F electric over F gravity equal tension force sine theta, tension force cosine theta, and you can cancel the tension force. And sine theta over cosine theta will be tan theta. Now what else we know? Electric force, Fe, here this is electric field. So how we relate those two? By the equation, electric field equal electric force over charge, or electric force is charge multiplied by electric field. So I replace this one with QE over gravity force is mass multiplied by acceleration, and this side is tan theta. Now what's the question? Find the Q. I put it a small q, but I mean the capital Q here. Doesn't matter, I can change it to capital Q if I want. So I'll say that capital Q I mean is small q. Q is unknown, electric field is known, 12,000, mass is known, 1 gram, which is 1 over 1,000 of a kilogram. Now I must know tan theta or theta. If I know theta, I can find Q. Theta, we find it from the geometry here. Look here, this is the top, angle theta here. L is known, Y is known, so we can find H in this triangle, right angle triangle. And if you know H, you can know theta because you'll have two sides known. So what we say, how do we find H? If I say L, the total, minus Y is H. So H, the side of the triangle, is equal to L minus Y. And what is L minus Y? And L and Y are known. L is 0.5, Y is 0.12. So we find that H is 0.43 meter. This is H. So now you know H and L, you can find theta using cosine theta. So if we say here cosine theta is H over L, 0.43 over 0.55, and you take the inverse, you find that theta equal 38.6, nearly 6 degrees. Now you can substitute here for theta, you get a Q. So Q multiplied by E, 12,000 over the mass 10 to power minus 3 times the gravity acceleration 9.8 equal tan of the angle 38.6, and you find the charge Q, which is 6.5 times 10 to power minus 7 coulomb, and it's a positive charge, as we said. So this is like again a review question of what you learned in physics 1 and mechanics, equilibrium, but here use it for electric force and charges. I'll show you the solutions again here on another page. Question 40. This will help you as well. Right. And this question 44, practice problem of chapter 21, electric field. What we have here, we have two thin non-conducting sheets of charges A and B, as shown in the figure. Here we have the figure, we have A and B, two thin non-conducting sheets, and they are charged both and are parallel to each other vertically. Now the sheets have surface charges densities. So the surface charge density for the plate A, positive 3.8 nano coulomb per meter squared meter. This is area, charge on area. And B has a negative charge, minus or a negative 1.9 nano coulomb per meter squared, again area respectively. This is A, this is B. The question says find the ratio between the electric field E2 to E1, E2 over E1, so 2 over 1. The magnitude of the electric fields in region 2, E2 means in region 2, this is region 2 between the plates, to region number 1, which is behind the positive charge sheet. So E2 over E1, not E1 over E2. We need the ratio between them. So how we find the ratio of the electric field? Now to solve this question you have to remember something very important which you learned about a non-conducting disk, charge disk, which we studied in the beginning. Okay, so let's start here. Looking at the question, we have two plates, one charge positive, one charge negative, a distance here between them. This area we call it area region 2 between them. Behind the negative region 3 here, and behind the positive region 1. The question says find the ratio of the electric field E2 over E1. Now when we have non-conducting sheet and it's charged, we know the electric field in front of it or behind it, behind the sheet, which is the thin sheet. The electric field is known, the formula is known, and we discovered the formula when we did the question of a disk charged, a non-conducting disk. And we took the case when we want to find the electric field very close to the disk. So we found it is constant. It doesn't depend on how far the charge is from the plate, as long as it's very close. So for non-conducting sheet, you must know that the electric field is always equal to the charge density, the surface charge density, over twice of epsilon naught. This is always needed and known for non-conducting sheet. The electric field is sigma over 2 epsilon naught. We need this equation later on when we study capacitors. So this is like the electric field, and this is similar to a capacitor, positive charge, negative charge, with a distance between them. This is like a capacitor, so I can tell what's the electric field between them. So now the question is not about that. The question is, what is the ratio between the electric field between the plate and the electric field behind the positive plate. Right, let's take region number 1, and let's say I want to find the electric field here. Here, what's the electric field of the positive plate here? It's equal to E sigma of the plate over 2 epsilon naught. That's if I have just this plate. Which way it is? Because remember, we put a test charge which is positive, so it means E for the positive plate will be a repulsion this way. So this is E of the positive plate. Now the negative plate, what does it do here? It has an electric field, but which way? Negative, positive, it's in this way. E negative. So now what's the total electric field here? 2 opposite electric fields. So the net field, which here is E1, is called E1. We can find it by subtracting the 2 fields. Which one is strong? Of course, the positive or the negative? The positive, because it's closer to the positive, far from the negative. So we'll say E positive minus E negative. And E positive or E negative always depends on sigma and epsilon. So for the positive, we say sigma of the positive, which is A, sigma A, over 2 epsilon minus E negative, sigma of the negative, which is B, 2 epsilon. This is electric field region 1. Now we have to find the electric field region 2 here. So if I take again a positive test charge, and I draw the effects of both plates. Positive, positive repulsion. So E A or E positive is this way. Negative, positive this way as well, attraction. So E2, the total here, would be E net is E2. This is for region 2. Here was one for region 1. So E2 equal additions of positive electric field plus negative electric field. And remember, both are constant and they depend on sigma. So sigma A over 2 epsilon naught plus this time sigma B over 2 epsilon naught. So this is the electric field at region 2. Now all what we need to divide these two. So E2 to E1, this ratio, to this one. Of course, here you can unify this or simplify it. I'll do it here. Sigma A over 2 epsilon naught plus sigma B over 2 epsilon naught. And E1 here we have sigma A over 2 epsilon naught minus sigma B epsilon naught. Here you have 2 epsilon naught common. So you just have to add sigma A plus sigma B. Here as well you have 2 epsilon naught common, but you'll have subtraction, sigma A minus sigma B. Cancel these two, and then just substitute the values. So here you have sigma A plus sigma B over sigma A minus sigma B. Sigma A and B are known, given, so substitute them. Don't put the sign here of the sigmas, because you are interested in the values, absolute values. So even if sigma B is negative, but here you're talking about the values, so put the values only. Which means now we have sigma A 3.8 nano plus 1.9 nano. So nano here, I can put the nano outside. Times 10 to power minus 9. Of course here I'll have nano as well, but below I have 3.8 minus 1.9 nano. Nano with nano cancel. So you add over subtraction. You have the E2 over E1 will give you 3. The final answer is 3. Okay. So this is how you solve this. Just pay attention to what I said. Non-conducting sheet has an electric field constant and it's always equal to sigma over 2 epsilon naught. It's a constant. It doesn't change with a distance away. So we find the electric field here by finding the effect of this sheet and effect of this sheet, and they are opposite. Here they both have the same direction. You add them, here subtract them, and the total here divided by the total here gives you a ratio of 3. Good. Now we'll do question 45, practice problems of chapter 21, electric field. Question 45 says there is a helium nucleus, of a helium atom is located between the plates of parallel plate capacitors. So we have 2 parallel plate capacitors, like a capacitor, and we put a helium particle, a nucleus of helium between them. Now the nucleus has a charge of 2 electrons, but positive, because it's the nucleus, proton. So it's like 2 protons plus 2 E. This is the charge of the nucleus of helium. And the mass of the nucleus is 6.6 times 10 to power minus 27 kilogram. So we know the mass and the charge, and it's positive. Now the question is, what's the magnitude of the electric field E? Remember, there will be an electric field between the plate. This is positive, this is negative, so you have an electric field. Such that the electric force, so this electric field will create an electric force on the nucleus here, on the helium nucleus. So how much electric field we need? So it generates an electric force here, which balances the weight of the helium nucleus. The helium has a weight, force of gravity down, and here the electric field will create an electric force which balances it out. So the particle will not fall on the plate, or the nucleus will not fall. So it reaches an equilibrium state, stationary. So how much electric field we need so the charge will not fall? This is a good question, and it's got many applications. It's used in Millikan experiment as well. So let's see how we solve this question. So here we have the negative plate. Here we must have the positive plate. Now, why this one has to be positive? Because the charge is positive. So if the charge is positive and this is positive, we'll have a repulsion force up. And we have the force of gravity down, so there is a possibility to balance these forces, and we keep the nucleus hanging here. It doesn't go up or down at a state of equilibrium. But if you reverse the polarity, if this is positive, this is negative, positive with positive repulsion, and the weight is down, so you have both forces down, so there is no equilibrium, so the charge will fall. So the idea here to say that these two forces are equal. At equilibrium, forces are equal. We have forces up, forces down, no forces to the right or to the left. So we have the force of electric force up. The value of it must equal the value of the force of gravity, Fg. Now, electric force, how we find it? If we know the electric field, we can replace it with the equation of electric field. So electric force is equal to the charge multiplied by the electric field. Gravity force is mass G. Don't forget, E equal F electric over charge. So Fe is charged by electric field. So this is my equation here. Now the question is find the how much is the electric field? E. So E from here is mg over q. The mass is known, 6.6 times 10 to the power minus 27 kilogram, times the gravity acceleration 9.8, and the charge is twice of this charge of an electron, but positive. So we have twice times the charge of one electron, but positive. Everything is known, and this is equal to 2 times 10 to the power minus 7 Newton per coulomb, the amount of the electric field, which makes the charge balanced, not moving up or down. So you have the solution as well given to you.